Hey guys, so today I'm bringing you a video on how to change the clock frequency on the STM32. This course specifically, this video is specifically going to apply to the STM32F1, the little blue pill that everybody likes. Uh, I say that because the clock tree among different STM products kind of differs. So like the G0 will be different than this, which will be different than an F7, for example. But I think if you can understand what's going on here and how to use the different tools together, then you can kind of make sense of what's going on in your microcontroller, and you can know how to find the right settings that you need. I will be using CubeMX, not to configure it, but to show you the clock diagram and show you what it is that we're changing in our code at the register level. So I'll use that. I'll also have another little image I made to kind of help clear things up. You'll also need the programmer's manual, and you'll need the obviously the reference manual for your specific chip. Um, and that's it. I'm gonna show you guys quickly. Here's my blog. So if you don't have the programmers or the reference manual, you can find it actually here. If you go home to this blog entry, here I have a link to the reference manual and the programmer's manual. And there's actually two programmers manual for the F1. There's one for the Cortex M3 and one for the actual microcontroller, because we need to access the flash registers, which are not fully defined in just the reference manual. Here in my blog, I have all the code where you can copy and paste it. That's what you want to do for this video that I'm about to make. Okay, guys, so go to the blog, check that out if you want to maybe read this, because I might stumble through my words while I do this video, but here everything is explained thoroughly. I'm using Visual Studio IDE now with the Visual GDB plugin. I bought a license for that because I really love this IDE. I still think Kyle is the best and the industry standard. Unfortunately, Kyle, for debugging has a 32 kilobyte limit. For G0 and L0, I think it's actually free, the whole IDE. But for other chips, it really is limiting unless you buy a license. A license for that is really expensive. A license for Visual GDB is like $100 or $50 if you get a student discount. So I've switched to using Visual Studio. So far it's working great for me. I love it, and it's such a sexy modern IDE. Kyle is looking kind of old lately. All right, so let's get started. Here's my program. It's really nothing. These includes are just for something else that I was working on, testing out some libraries here. The heart of our code is this function set to 72. I call that function here in my main. My for loop has nothing, so everything is in this function. Even though I call it set to 72, I'm gonna actually set it to different values so you can see. Let me see if I can change the values. There you go. Okay, yeah, this was something else I was showing. Okay, so this actually sets my microcontroller to 28 megahertz. If I highlight this, right now it's in debug mode, so I'm highlighting this and it's showing me a value of 28. So it's setting the microcontroller to 28 megahertz. That's the value that I'm using. I will show you how to set it to 72, or basically any value that you want, as long as it's in phase with the oscillator, obviously. Okay, so let's get started. The very first thing we're going to do is we're going to actually turn on the external crystal, and that is what you see right here. Here's a little, this is just a copy and paste image of this clock tree on the STM32 cube thing, right? But I can't make this bigger, so kind of did thing here where I highlight. This is available on my blog too if you want this image or something. So anyways, what we're doing here is we're enabling this, and ignore the numbers. This is just from left to right. This is not necessarily the steps in which we're going to do things. So the first thing we're doing is enabling the high-speed external. Now, another thing you need to understand, I guess I'd like to kind of go off topic, but not really. The high-speed external, your external clock to your microcontroller, it doesn't necessarily have to be a crystal. It could be a MEMS oscillator, which are becoming very popular because they're really tiny, very accurate, and you don't need capacitors, so you're lowering your parts count, right? Your external oscillator can also be the output clock of another microcontroller, and you just enable the output clock on it. It takes its own clock and it outputs it, whatever it's running at. It outputs that, and you can feed it into your own microcontroller. So the external oscillator doesn't necessarily have to be crystal. In fact, that's what these boards do. These boards, well, not all of them, but some of them with the integrated ST-Link, instead of having two crystals, one for the ST-Link, one for the other chip, they just have one crystal and they have the ST-Link output its clock to the target chip. And then sometimes there's a solder bridge in the back or something where you can make that connection, and it'll make the connection from this master output clock into the crystal pins for this for the target chip. So that's just a little side note. So that's the first thing we're going to do in our code, enable that high-speed external, and that can be found in the RCC register, in the control register of the RCC peripheral, and that is bit 16. So we'll go to bit 16, we'll see that we're going to turn that oscillator on. Now you have to let that stabilize. You have to make sure it's actually on and ready. So to do that, we use bit 17, which is a flag, and it's simply going to tell us a 1 right there when the high-speed external is ready. So that's what we do in our code. We turn it on, and then we wait in this while loop until that's ready. Now ideally, if you're a good programmer and you want to make a robust system, what happens if it's never ready? Then you're going to be in this while loop forever. So you don't want to do that. You want to actually put a counter or put a for loop here instead and have it check that variable, like, I don't know, make it go through the loop like 500 times or something. And if at the end of that loop it's still not ready, then there's something wrong. Then you can kind of exit all of this because it's not going to work. So then, you handle that accordingly. But for simplicity's sake, I haven't done any of that. I'm just showing you the bare minimum. I know my crystal works and everything's fine, so it's going to go through this loop just fine. If I turn on the crystal, I make sure it's ready. The next step is this flash ACR prefetch buffer. The flash register is defined here in, I'm not even going to look for it. It's here somewhere in your in the reference manual, but it only shows you one register. It only shows you this flash ACR register. The programmer's manual for the STM32F103 shows you the entire flash registers. So that's good. And it also shows you option bytes, anything. So this is a good document to have. What we're going to edit in this flash register is, for now, this prefetch buffer. That's bit number 4. Prefetch buffer. Now, what is that? That is, according to this, it's the implementation of this prefetch buffer makes a faster CPU execution possible, as the CPU fetches one word at a time with the next word already available in the prefetch buffer. So if you think about the word prefetch, it's fetching the next instruction it's going to execute before it's even done with the current one. And that's what that does. And since we're operating our microcontroller at a faster frequency, then that obviously is a beneficial thing to do. It says this implies that the acceleration ratio will be to the order of 2, assuming that the code is aligned to 64-bit boundary for the jumps, etc. That's pretty cool. So you want to do that. Also, if you look at this ACR register, by default, that should be on. Okay, it's going to be on by default according to this document. So I did it just to make sure, right? But it should be on anyways. Okay, so what's the next step? The next step is we're going to change the flash wait states. We need to add some latency. Why? Because our microcontroller, the flash can only be written to and read from at a certain speed. And obviously, if we're maxing out our chip or whatever we're doing, we're not going to be able to write to our flash at that high speed. So we do have to add some latency so we can wait for those operations, those read and write operations to take place. And again, this is in that flash register, which is better defined in the programming manual. So that's this right here. And that's telling us that if our system clock is going to be between 0 and 24 megahertz, we should have 0 wait states. If it's going to be between 24 and 48, we should have 1 wait state, and 2 wait states if it's going to be between 48 and 72. In my example, I'm doing it to 28 megahertz, so I'm going to use 1 wait state. So then we're going to just put the value 1 right there. So first thing I did was clear it just to be sure. I'm not sure if it's got anything else in there or whatever. So the point is I just clear it first and then I write the 1 to it. So that's going to be a 1 in that latency bits. The next thing we're going to do is the heart and the meat of everything is we're going to edit the RCC register to get it configured to our actual speed that we want. This function, this line just clears some bits, these 3 bits right here. So before I write these bits, I'm first clearing all of them. So that's all this line does. It just resets all of those to 0, just so that they have a known value. Okay, so let's go to this image. So we've done this, right? So the next thing that comes here is this little divide by 1. This little divide by 1, this section is the pre-divisor, or pre-div 1 is what the datasheet calls it. But the actual bit is not called pre-div 1, it's called x pre-div some crap. It's called this PLLXT pre. That's what it's called. So how does that bit work? It's really retarded. Let's go here. Bit 17, the XT pre. So it says set and cleared by software to select the least significant bit of the pre-div 1, that little divisor thing I showed you. It is the same bit as bit 0 in the configuration 2 register. So this saying whatever you put in this bit is the same as this bit right here, right? Pre-div 1. So whatever that other bit I just showed you is, that value will always match what's in here. So if this is a 1, that other bit will be a 1. This one. So if you clear this one, you also clear that other bit 0, this bit. Now the interesting thing is that this configuration 2 register, CFGR2, that does not exist in our code. If you were to write a 2, it doesn't exist. So we don't have that second configuration register in the RCC. So what the hell, right? So then, go back here. We keep reading about this bit. It tells us that if bits 3 to 1 in register configuration 2 are not set, okay, so if they're not set, well, I'm gonna just assume they're not set since they don't even exist on my chip. Excuse me. Then this bit controls pre-div 1. If pre-div 1 divides its input clock by 2 when the bit is 1, or not when the bit is 0. So what this is saying is that this pre-div 1 will divide the input clock by 2 when this PLLX pre-bit is 1, or not divided by 2 when the PLLXT pre-bit is 0. Basically, in English, when you put a 1 into that PLLXT pre-bit, when you put a 1 in there, it takes this and it does divide it by 2. When you put a 0 in there, it takes this and does divide it by 1. Okay, and you can see how it changes the clock that's coming out of the PLL, right? See forward because it's taking this and it's dividing it by 2 or dividing it by 1. Another thing you have to be mindful in the datasheet, anytime it says divided by 1, like here in the settings, in the datasheet it doesn't say divided by 1, it says not divided. Because mathematically speaking, if you're dividing by 1, you're not really dividing anything, right? So if I'm going to set my clock to 28, let's change this to 28. This has to be divided by 1, in other words, not divided. So we're going to maybe not divide that. Oops, what another? Shut up. Let me change this to 28. There you go. Okay. This doesn't need to be divided. Okay. So anyways, back to this. This needs to be divided by 1. So to get divided by 1, we're gonna put a 0 in that bit, because that's what it says. When it's a 0, it is not going to divide anything. So I take that bit and I turn it into a 0 right there. The next thing we're going to do is right here. This PLL, in what source are we going to use? The high-speed internal or the high-speed external? Now in the datasheet, they don't call it the high-speed external. They call it pre-div 1, which is this right here. So are we going to take the clock from pre-div 1, or are we going to take the clock coming through the high-speed internal? PLL source right here, bit 16. That is right over here. Clock from pre-div 1 selected as PLL. So that's what we're going to do. The clock from pre-div 1. We're not going to use the clock from the high-speed internal. So we're going to put a 1 in there. So that's what I do in my code. I put a 1 in the PLL source. The next thing we're going to do is this right here, this multiplier. Since I'm setting it to 28, this multiplier is going to be 7. And this is a screenshot I took of this. So as you can see here, it's set to 7. We're going to go into this PLL multiplier. Where the hell is it? Oh, 28 to 18. Oh look, this is what I was telling you about microcontroller clock output, that MCO. So you can tell that microcontroller which clock to output, and it'll output it on a specific pin, and then you can use that to feed another microcontroller. Anyways, this is what we're looking at. So we're gonna do a multiply by 7. And this is not where a 1 equals multiplied by 1, a 2 equals 2. No, these are specific values that don't necessarily match up to the number over here. So this number right here is 1, 2, 4. This is number, what, 5? So this 5 will be multiplied by 7. You put a 5 in here. Multiply by 7. So that's what I do here. I change the multiplier to 7. The next is this H. These are the because they're all kind of named similar. H pre, PP pre 1, PP pre 2. So H, just remember that H pre is the HB prescaler. So HH, right? And that is basically this right here. We're gonna set that value to divide by 2. So that's what I do right here. AH pre, I divide by 2. As far as datasheet's concerned, that looks like this. H pre divided by 2, so it's going to be that value in there. Now if that were to be divided by 1 for some reason, there's no divided by 1. That's equivalent to not divide, right? Because mathematically, like I just said, you divide by 1, it's like you're not dividing, so you would put all zeros. Or it doesn't care what the bottom bits are, it cares about this top bit being 0. But we're going to use divide by 2. So that AHB prescaler, H pre, is going to be set to 2. So 2. Then the APB1 and APB2 bus are going to be set to 1 and 1. So here the PP, the P pre 1 is APB1, the P pre 2 is APB2. So both of them are going to be divided by 1, div 1, or aka no divide. So that's that. So now you've configured all of the these settings, right? You've configured this, you've configured this, configured that, you've configured that, and that. The next thing we're going to do, well, obviously this, but we have to turn it on, right? Because you have to do all these configurations while the PLL is off. So that PLL has its own bit to turn on and ready flag in the control register. You go back to the RCC control register and you turn on the PLL with this bit, just put a 1 in there. And just like the other bit for the high speed external, it has a ready flag that you're going to keep polling it until it's actually on. So PLL on, and then PLL locked. Locked means that it's ready. This is called a phase locked loop. So that's telling you that it's locked in phase with the the external clock. So there you go. It's on. It's ready. Once you do that, once you turn it on and once you check it's ready, then you can select it as a source, and that's what I do here. First thing I do is I reset. I'm resetting these bits right over here. So this these last four. Scroll. Okay, so these bits 1 and 0 will select which clock you're using. So basically what we're doing now is this step right here. We're selecting the clock, right? Because before we select this PLL here, we need to make sure it's ready. We need to make sure all these things are set. Then we can switch the clock from the high-speed internal that it was using in my case, for example. So we're doing that step right now, and we're gonna select the PLL as the system clock. So you're gonna put a 2 in there. Again, this is very important that you have to wait for the PLL to be ready, to be set as a system clock. Not to be on, it's already on, but to be ready to switched over as your system clock. So then you're gonna pull this flag or this status bits, and you're gonna search for this pattern to make sure that PLL is now being used as the system clock. So I reset it in the beginning. I reset these 2 bits here, and then I select the PLL as a clock, and then I wait for it to be actually used as the system clock. Once that's done, it's done. Your thing is set. Your clock is going. Once you get past this while loop. It's also very important that you call this function right here. This function updates this variable, system core clock. This variable is very important to CMSys functions. It's very important to how to cube stuff or to LL libraries, whatever you're using. It's very important that they know this variable is correct. This basically tells you what speed your microcontroller is operating at. And this is not a variable that you're gonna go and just set it equal to something, by yourself. You're not gonna type this here and say system core clock equals whatever you think you're setting, because you know why? You could actually mess something here up and you think you're setting it to, let's say 72, but let's say you mess something up and you set it to something else. So not only are you lying to yourself, but you're also lying to the microcontroller now, and it's gonna just mess things up, right? So to update this variable, call this function. That is its sole purpose is to look at all the registers in the RCC, and it will calculate what speed your microcontroller is running at, and it will update this variable accordingly. So you can lie to yourself, but don't lie to the microcontroller. Let it do its thing and figure out what's really going on. Okay. So always call this at the end of your microcontroller frequency adjustment, and do not call sysdig config or anything that uses this variable until you've called this, right? So it's gonna be 1, all of this, and then 2, and then 3. You can start using other things that depend on that variable. All right, guys, like I said, this is all in my blog. If you want to copy and paste the code, it's all there. I didn't even prove it to you. So let's run this debugger. Let's see what it shows this variable to be. If you can see that, I'm not sure. You might have to max out the YouTube screen, but this right here says 28 million. So this value is 28 million. So let's change the clock now to 72. Let's see how easy it's going to be. So this is 7211, right? These two. Let's see if we change it to 72. What changes? So now it's 121, and this changed to 9. So let's change the multiplier to 9. I know that the macro is like this. The H pre is, what was the H pre? The H is 1. So that's now 1. And APB1 is now divided by 2. APB1, this one is now divided by 2. And that's it. I would also have to change my wait states to 2. because that's what it said in the data sheet. If it's between 48 and 72 megahertz, you're gonna need 2 wait states. So let's run our code, debug. I have a breakpoint over here, and now this clock is now 72 million. So it's 72 megahertz. There you have it, guys. Proved it. Like I said, code is all in my blog. Copy and paste. If you need certain documents, I have an entire other post here about documents that you need. People sometimes on YouTube comment that I should email them the reference manual. Like I got it from my secret connection over at ST Microelectronics. No, guys, just Google it. Come on now. But if you don't want to Google it, then here are all the important documents you need. Programmer's manual, data sheet, API drivers, manual, hardware design reference manuals. It's all there. And that's it, guys. I hope you enjoyed that. I hope it made sense. I hope I didn't mess anything up or whatever. Enjoy.